Along with him, I also welcome our HOD who is chairing this session, Dr. P.K. Swain sir. He has been the faculty member of our basic and applied science, and he is currently the HOD. Before that, he was the Dean R&D of the institute, and he has done his research from IIT Kharagpur, and he is in service of NIT Arunachal Pradesh for the past 8 years. So, and I also welcome all the participants after a great lunch. Okay, so now I hand over this session to our expert, sir. Please, sir.
Okay. Thank you, Dr. Banav. Now, I'm gonna continue with the docking things because in the morning session you have a lot of questions. You asked a lot of questions about molecular docking, and I say that many of them should be answered in the afternoon session. So I will try to cover other aspects of molecular docking. Okay. So over the years, okay, so basically computational biochemists, they have developed numerous models to capture the key elements of molecular recognition process. Okay, so although they are very simplified, but these models are proven highly useful to the scientific community. And I really like this comment by George Box. Okay, all models are wrong, some are useful. Well, models means you are making some approximations, and the accuracy or how useful it is, it depends on how good are your approximations are. Okay, and I also tell you that all the approximations that you make to make a good compromise between speed and accuracy. Only accuracy is not enough. You need also good speed up. When I say speed up, it means the computational speed up, okay? So speed up could be from utilizing the parallel processors or the GPU cores, as well as also the method that you are using, okay? So we will talk mostly about the different methods that can be used to gain significant speed up. So over the years, since 1890 to 2003, so mainly 3 different models are available for molecular docking. Okay? First one is the traditional lock and key model. And then in 1958, there was Induced-Fit model. And then 2003, this Conformational ensemble model came out. Okay? So the lock and key theory is very simple. So here, that biological systems, basically you can say that a substrate fits into the active site of macromolecules, just like a key fits into a lock. Okay, so you have lock and you have key. So your ligand is your key, and the protein target is your lock. It just fit, just like that. Okay, that's what we saw here. Now, this thing actually becomes a bit difficult. For small molecule, this is fine. Okay, when the ligand molecule is rigid. Now, for example, you want to study the host pathogen interaction. I said how they are recognizing. So now I said that the host pathogen recognition is mediated by protein and sugar molecule interactions. Now, the sugar molecules, or carbohydrate we call it, or glycan, so these are very flexible molecules. What I mean that at room temperature, it can have multiple conformations. And each conformation of the same glycan can bind to different protein. So in the case of protein glycan recognition, you have the lock, but you have bunch of keys, and each key can open different lock. So that is a difficulty that you face in modeling protein carbohydrate recognitions event. And that's why it is very difficult to study the protein carbohydrate interaction in experiment. If you want to perform X-ray crystallography study, it's very hard to get the required electron density. So that's why you can use predictive tools such as molecular dynamics based method to predict the crystal structure as well as the interactions actually. Okay. But generally, when we talk about protein-drug interactions, so traditionally it is lock and key. Okay, you don't have multiple keys. You have lock and you have one key. And then there is induced-fit theory that comes. So often you know that the protein actually, or the receptor, undergoes some kind of conformational changes. And so that the fitting between this receptor and the ligand is perfect. Okay, so that adjustment is gone. So that is called the induced-fit theory. So here both the ligand and the target mutually adapt to each other through small conformational change. Conformational change means the structural changes, okay, until an optimal fit is achieved. So that you can see from this figure, you can see that how both this ligand and the protein, or the target actually, both have undergone some minor conformational changes so that the binding is very strong. And the third is the conformational ensemble model. Why do you need this model? Because the proteins, as I said, they have some plasticity. Okay, so they are very flexible molecules. So at room temperature, it can have multiple conformations. So instead of taking a single target protein, okay, so you can take the multiple structure or the multiple copies of the same protein, and then you can do docking study. Okay, the same protein but multiple copies, and each copy is different from the other copy. Now you dock your molecule to the binding site and evaluate the energy. So at least then you compare the energy and then find for which protein conformation you got the lowest binding free energy. That is the more negative value that you are getting. So that would be your optimal case. Okay. So so this way, basically, it helps you also to take into account the effect of flexibility of the protein molecule. Okay. But you see that over this from 1890 to 2003, when you have all these different models, from shape complementary to induced fit, and then this conformational ensemble models, we are increasing the complexity in our model. At the same time, we are increasing the computational resources also. Okay, so generally, I will tell you actually what are the different how it. So generally here, you know, when you consider all possible flexibility of proteins, okay, the number of degrees of freedom will increase significantly, and that's why you need a lot more computational resources. So adding protein flexibility is not that easy. It incurs some, a lot of computational resources, and your overall calculation would be slowed down. And the industry problem is that they cannot afford time. They are always running out of time. You have to give them the result very quickly. So that is one issue. Okay. Now, the different things we'll talk about this molecular complementary in computational docking, that you see that there is this complementary, actually it binds like that. Okay, so the complementary could be two different types. Okay, it could be step complementary, and other could be the chemical and physiochemical complementary. In step complementary, that you can see in this below left hand figure, so that is the primary criterion for evaluating the fit in the computational docking of two candidate structures. Okay, so that's how you check the binding cavity, how does it look, and then you orient your ligand accordingly and try to fit into that. Okay, so that is very important, the visual inspection of that. Okay, accordingly you can do it. The other thing is the chemical and physiochemical complementary. Well, that's are also important criterion in the docking between the candidates, because you know that Well, some maybe hydrogen bonding donor from the receptor side is there. So of course you would like to orient your ligand such a way that the hydrogen bonding acceptor of your ligand, they are placed nearby so that they can form hydrogen bond. Or there could be aromatic interactions, or there could be hydrophobic interactions also, or electrostatic if there is a positive charge from the ligand is there. So you should try to place that part close to the negative charge amino acid. So those kind of things you have to take into account. Okay, so that is how you can quickly actually develop drug. In this respect, I just want to tell you this: the flu, for common flu that we have, this drug called Tamiflu. Okay, so Tamiflu is entirely designed in computer, and they design it very quickly. So they just look how the sialic acid, which is the substrate actually that binds to the binding pocket, they just look at it, and it's a carbohydrate mimetic. Sialic acid is a glycan, a carbohydrate molecule. So then you just copy it, and they say that, oh, there is one particular charge amino acid is there. So what they did, then they just add another negatively charged functional group to that, and then they form hydrogen bond, and that makes a very good drug actually. Okay, that's how you got the drug called Tamiflu. It's a very interesting study, and within 3 years they just from concept to the marketing it takes. Okay, that's one of the successful thing. And recently Schrödinger, in collaboration with Sanofi, they also designed one drug molecule for cancer therapy. Okay, so that also they find it within 3 years. So that will soon be marketed actually. So the computational, all this docking method have immense potential to reduce the time frame from 10 to 12 years to within 3 to 5 years. That can be done. Use computational, all these computational methods is very rigorously as well as in a sensible manner actually. Now, one thing just I have to tell you, the energy dictates this molecular association, that you should know. Okay, the ligand you can place in the binding pocket in different orientation, and each different orientation will have different energy. Okay, so that is shown in the right hand panel. But the base binding is the one for which the energy is lowest, the more negative. Okay, that is the shredded, olive color shredded, that is, so that would be the best pose. So what you need to do is basically you orient your molecule in the binding cavity, okay, and then evaluate the energy. Then you check for which orientation you got the lowest energy, and then that is your perfect orientation. But this may not always be the case. I'll show why. Okay, sometimes the lowest energy does not mean the best binding. So now for this docking study, there are two important aspects, as I said. One is the scoring function, and the other is the search method. The scoring function, basically that roughly approximates the binding affinity of a ligand to a protein, given the binding pose. Okay, you generate a pose by orienting it and try to evaluate the energy. So that is your scoring function. That will be done by it. And the accuracy of your prediction will depend on the scoring function. How accurate is your scoring function? And then there is a search method. So the search is for the base scoring binding pose for a given ligand. That I said that you have to orient your molecule in the binding cavity. Okay. So this is basically searching. You are searching the conformational space. Okay. And now, if you can search all possible conformational space exhaustively, then that will help you to predict the binding pose accurately. If your method is not good enough, you cannot basically search the entire phase space or the conformational space, and then of course, basically you are searching only a subspace of the total phase space. Then you are predicting, okay, this is the correct pose. It may be correct or may be wrong. You don't know. So you need to have a searching algorithm that will help you to search all possible conformations. That is the orientation of the ligand in the binding cavity. Okay, so that is very important. So these are the two main factors in molecular docking, and the accuracy depends on these two part actually, scoring function and the searching algorithm. Okay. Now the most ligand docking method that assume that the protein is rigid. Okay, and the approximate binding site is known. Okay, so that is, one is looking for ligands that will bind to a particular site on the target. Now you know that in reality, ligand is flexible because it's a small molecule. Small molecules are always flexible. Okay, proteins are also mobile. Proteins are also flexible. Okay, and then the water molecules, they also play a major role in determining binding affinity. As I told you that sometimes the receptor, that is the target protein, and the and your ligand, they form hydrogen bond via these water molecules. So the water act as a bridging molecules. So you need to take into account all these things. Then only your prediction will be good enough, and experimentally you can validate it. But we don't do that. We make approximation. We said the protein is rigid because that makes our life much more easier. Okay? And instead of all these approximations, still docking is useful. Okay? And then, as I said, that the scoring function determines the binding energy, and the better the scoring function, better will be the predicted binding energy, and that will help you to correctly rank all the ligand molecules that you are testing. Okay, so if you can predict the ranking very accurately, then of course you can then choose, okay, these are the 5 molecules out of 100 or whatever that you want to perform experiment with these 5 molecules. Okay, so that is very important things. Now the question is, how would you take into account the molecular flexibility in protein drug docking? Okay, the mutual adaptation of a ligand with its receptor is crucial to understanding ligand binding and protein function. Okay, and one of the major challenges that you face in molecular docking is how to account for this adaptation in docking calculations. So generally 3 ways we do it: the rigid body docking, and rigid receptor but flexible ligand, which is more common, and the third one, which is the best one, is the flexible receptor, flexible ligand. In rigid body docking, you ignore the flexibility of both the ligand and the receptor. You treat both of them as just rigid body, and you just dock them. So that was the first model. Okay, it's very easier to do it. So first set of models were like that. Okay, now you know that in many of the cases, when a ligand or a drug binds to the target protein, then the side chain of the amino acid present in the binding site, they undergo conformational changes. So if you do the rigid body docking, then you are missing that part. Okay, so the predicted binding energy from docking calculation would be wrong. And if you then go ahead with those wrongly predicted structure, go ahead with experiment thinking that, oh, I have got the drug candidate, then that is actually wrong. Okay? Highly possibility that you will end up with something wrong, and you have to, in the middle of your all these experiment, you have to scrap it. Then the semi-flexible model, okay, where the receptor is rigid and the ligand is flexible. Okay, so this is a semi-flexible model, and this is, of course, relatively better than the rigid body docking, but still it is not the perfect. The best one is the third one, where you let the receptor and the ligand both be flexible and do the docking. Let the protein also undergo conformational changes due to the binding of the ligand. Okay, so that would be the best thing, but it is also very difficult to do it. And with all these, basically, your computational time increases significantly. Okay, the rigid body docking is the fastest and simplest method. Okay, most current approaches treat receptor as rigid and ligand as flexible. This is a good compromise between speed and accuracy. And the third one is the advanced approach, that is the receptor is flexible to some extent. Entire flexibility of protein, you cannot treat it in molecular docking. No, you cannot do it. You can do it by molecular dynamic simulations, okay? But you can, of course, make the ligand more flexible. So now if you, basically the graphically same thing I have shown here, how the complexity increases with the basically addition of flexibility in your systems. So generally, this thing for the rigid body docking, you have 3 + 3 degrees of freedom. Okay, 3 that comes from the position XYZ coordinate and 3 from the orientation. Okay, and for flexible, actually you have 3 + 3 + NR. Okay, that's the interactable problem. So NR is the number of flexible bonds. Now proteins are big molecules. Okay, moderate size protein has say 2000, say 300 amino acids. So you can imagine how many bonds each atom can form. 3000 atoms, the residue means approximately you will have 5 to 6,000 atoms. Okay, so you can imagine how many bonds there could be. Okay, so that actually increases. So for rigid body, you have 6 degrees of freedom. For semi-flexible docking, you have approximately 1500, and for flexible docking, you have approximately 3000 degrees of freedom. And with that, actually, the computational resources, you need more computational resources, but it will be better. Okay. Now, of course, you cannot use this method for millions of compound when you want to screen. For that one, you should not use these things. For that one, you use the virtual screening method. Okay, that's the fastest method and simplest method. So now, what are the different ways you can handle ligand flexibility? Because I said that if you make both ligand and the receptor both flexible, that is the best thing. So how would you tackle the ligand flexibility? So this can be done using Ligand-Ensemble docking method, or fragmentation method, or stochastic conformational search method. These are the 3 different ways you can take into account. Okay, so Ligand-Ensemble is the easiest method. Okay, so here basically you create an ensemble of rigid and independent ligand conformations. So in the first step, low energy conformations of ligand are generated by conformational analysis. Okay, and then so all these things you can do it in computer actually. And in the second step, then you perform the rigid docking. So that means you treat the protein as a rigid, and now you have multiple ligand conformations. So each conformation you treat as a rigid molecule. Okay, then you do the docking. So that way, since for the same ligand you have created n number of copies, so that way you are adding, considering the flexibility of the ligand. Okay, so that's the way you can do it. You just dock it and then you find for which ligand conformation you got the lowest binding free energy. So that would be your best binding force. Okay. And then the fragmentation is basically you basically divided the ligand molecule into different rigid fragmentation. Okay, and then each fragment you dock, then the next fragment you dock and add it. You continue to do it until the entire molecule is formed. So this is the place and join and the incremental approach basically that you can take for docking each fragmentation and adding them together to make the complete molecule structure. Okay. So in the place and join method, you split the molecule into rigid substrate and each subpart is docked independently. Okay, and then you assemble. This is just like that. And incremental is basically you start with the initial core that docked in the active site, and the new fragments are progressively added and minimized. So the treatment is terminated when the entire molecule is formed. Okay. So these are the different ways you can take into account the ligand flexibility. Now, when you do this incremental algorithm, it is very important actually from where you are starting. You can see that in the example below, the initial rigid fragment has been docked 3 times, okay, A, B, and C. For each one, we have a set of potential solution that can be generated. Okay, and you see that how they are located. I mean, if you start from A, B, and C, okay, the same fragment you are starting, and but from different positions. So you can see that you are ended up with a final conformations that actually you end up is different. Okay. So solution with a bad score are eliminated. So this is basically you do all this A, B, and C, then you evaluate the energy. Of course, you will find that in the case of A, your binding energy would be the lowest. That means it will be the more negative value compared to B or C. So then you say, okay, that is the correct binding force or the best docked structure. Okay. So in the incremental algorithm, you see that there is a dependence on the choice of the first fragment to be docked. Okay. So which requires an exploration of several possibilities, and you have to explore all possibilities, and finally you have to decide which one is the best pose based on the binding free energy. And then there is this stochastic search algorithm is there. Here you just modify the conformation of the small molecule in the receptor site and assess it on the fly. Okay, there could be Monte Carlo based method, or you can have Brownian dynamics based method. Okay, so generally here you just change the torsional angle. Okay, you just change the torsional angle by 1 degree, for instance, or by 2 degrees. So all possible torsional angles you are changing it, and then you are evaluating the energy and find out for which case it is the lowest. Okay, so all these things should be done on the fly. So this is also very fast method, and also of course a very good method to incorporate the ligand flexibility. So now how to take or incorporate the protein flexibility. So protein flexibility, okay, so it is very easy to take the small atom fluctuations, okay, that you can solve by soft docking method. And then the problem is with the side chain flexibility. It is relatively difficult to handle. And the backbone flexibility, that's the hardest thing to do. And the domain movements are also very hard to model in the traditional docking method actually. Okay, but there, for practical reason, these 4 types of protein flexibility are there. So the soft docking basically, so here the simple approach to tackle the protein flexibility problem is the soft docking, and here you allows for slight penetration between the receptor and the ligand molecule. So here you can see that there is a bump. Okay, the ligand molecule is actually hitting the protein molecules, but you know that they cannot. I mean, atoms cannot collide with like that. It cannot bump. Why? Because of the Pauli's exclusion principle. If they come, 2 atoms come very close to each other, then because of the Pauli's exclusion principle, they should repel. Okay, so that's the quantum mechanical thing. So now how to tackle that thing? Of course, the van der Waals interaction. So Lennard-Jones potential has two parts. One is the attractive part. Attractive part will attract each other. And then there is a repulsive part. When they are attracting and coming to very close to each other, then the repulsive force will start working and they will be separated. So what we are saying that this attractive repulsive U is a very soft potential. So they will bump, but the class will just slightly, it will come back actually. It will hit and then come back. You are treating it softer. You are making it more soft. For example, think about it. Say it's a simple harmonic motion. Okay, the harmonic motions, you have this well, the potential well, it can be very strong, very narrow well, or it can have like this kind of wide well. If it's a wide well, then of course at the room temperature the atom can move a very large space. It can move like that. So you are allowing it larger motions. But if it is a very steep well, then they cannot move. The atom will just remain stick to the lower potential energy value. But if it is wider, then it can vibrate like that. So by softer potential, we are saying that basically the force constant that that modulates these things, you use it very small amount. Okay, so that you are giving it a wiggle, so that atom can wiggle around. Okay, so that is called the softer thing. So that can take into account that part. So that is exactly what we treated in van der Waals function. You can see that, especially the lower part, okay, generally we have a single point minima, but instead of that we have a flat minima that you can see that corresponds to epsilon in this figure, okay. In principle, the correct figure is the dotted lines, okay, where the minima is a single point. But if you look at these black solid lines, you can see that the minima is a straight line dotted, okay. So that's a softer thing. The protein, so you see there is no energy change. It can just move around this plane. The atoms can move around, okay. So that's why it is called soft potential. So that way you can take into account those bumping thing. Of course, it has problem solved and we can do it like, and then there is this protein side chain flexibility. So I said that the side chains are very critical for the binding of the ligand to proteins, okay? Because altering the side chain conformation in docking calculations enables the maximization of favorable interaction with the protein. And generally, the 60% of side chains modify their conformations upon binding. So if you don't take into account this thing, then your docking is wrong, okay? So that's why what we do basically, we use a Rodamer library. So analysis of side chain Ramachandran plot of PDB structure show that 17 of the 20 amino acids can be represented adequately by 67 side chain Rodamers. Okay, so then you just use this combinatorial exploration of these conformations, okay, using these different Rodamer chains, Rodamer library. So that will handle the side chain flexibility. And backbone flexibility, well, that is the greatest challenge in molecular docking. How you want to incorporate the backbone flexibility. So the traditional methods such as the systematic approach or stochastic algorithm cannot be used as a general method. Okay, generally you can use it molecular dynamic simulation that can give you the flexibility of both the ligand and the protein, both. Okay, you can have the backbone flexibility, you can have side chain flexibility, or you can have the domain movement also. All these things could be taken into account if you perform molecular dynamic simulations. Okay, so now you see that this is how the number of parameters actually increases and the CPU times that you require with the introduction of different level of complexity in your calculations. So if you use backbone and side chain flexibility, then you can see that how many CPU times hours you need and how the the parameters are also increasing. Okay, so that's why what we really do actually, we use semi-flexible method. Okay, so we let the ligand be completely flexible and only consider the side chain flexibility of the protein via rotamer ligand. You docked it. Now from that structure that you generate by docking, then with that you perform molecular dynamic simulations, 3 simulations, and check it. How? So again the structure will be relaxed and the ligand will move around the binding pocket and adopt the orientation for which the overall energy will be minimum. So if you take this 2-step approach, first you perform docking and then you perform molecular dynamic simulations, then you can solve this problem. Whether the domain movement or the backbone flexibility, side chain flexibility, everything you can take into account. So generally we take these 2-stage approaches. Okay. So another way of taking into account the protein flexibility is by using this multiple protein structure approach. Okay, that is called MPS approach. So I said that one of the way to treat ligand flexibility is by generating multiple copies of the same ligand. So do the same thing. For protein also, you generate multiple copies. Sometimes you can generate it by running small molecular dynamic simulations, or what you can do, if you search in the protein data bank, okay, where all the crystal structure are deposited. So generally for the same protein, you will have multiple structures available. For example, if you just look at the main proteins of, or the 3-cell proteins of SARS-CoV-2, this COVID-19, okay, that is the main target for designing drug. Currently, you will see that there are more than 10 to 15 structures are available. And all structures are different to some extent. Well, the deviation from each other would be maybe 0.1 to 0.2 angstrom, but still they are different because their energy would be different. So they are different structures. So instead of docking to a particular protein, why don't you dock your ligand to all these 20 or how many I don't know is available in the protein data bank? You are available to all possible proteins and evaluate the energy. Just check for which case the energy is minimal. That would be your best protein ligand complex structure. Okay, so that way also you can take into account the protein flexibility, and that is actually a little bit of easier, I would say, because you don't have to do anything because all those structures are available. You just download it and treat them as a separate target and just do docking. Okay. So this is the example that I showed from actually CDK protein. Okay, so for which these 7 structures are available. So I have superimposed each other, so you can see that the deviation that each structure is showing from one to other. So that means they have undergone some kind of small conformational changes. Okay, so that means you have taken into account the flexibility of the protein. Okay, so this is another way of taking into account the flexibility of proteins. So we have covered up all those things. So now the question comes, what are the different components of docking software? Okay, so generally the docking software can be categorized based on the following criteria. One is the molecular representation. Okay, so that is the way to represent structures and properties. It could be atomic, it could be surface, it could be grid representation. Okay, and then the scoring method that is used to calculate the binding free energy. Okay, so that is, it should be very accurate. So that's the method to assess the quality of dot complexes. It could be force field based, it could be knowledge based approach. Okay, so different things. And then the searching algorithms. Okay, searching algorithm means an efficient search algorithm that decides which poses to generate. Exhaustive search, Monte Carlo, genetic algorithm, simulated annealing, taboo search, all different algorithms are there. I don't want to go into details of those things, but these things you can use to generate a search algorithm. Okay. So in docking, it's a two-step process. First, you generate the pose. Okay. That means you place the ligand in the binding site, which is generally a solved problem. Okay. Now the second stage is the pose selection. Which pose to choose? Which pose has the, generally we choose the pose that gives us the minimum energy. Okay. And this is the hardest part, because which pose to choose is determined by the energy, and energy is determined by the scoring function. Okay, and scoring function means you have to take into account all possible interactions, okay, including the dipole-dipole interactions also. So how good you are making all those approximation, all possible for all possible interactions, okay, depending on that, the accuracy will depend. And here lies actually the main thing. Most of the software actually varies at this point. The scoring function that they are using to determine which pose to select. Okay. So the rigid docking with a series of conformers pose generation. Okay. Most techniques use this approach, and most techniques will generate the conformer internally rather than using conformers as input. Of course, that is the case because you just use single ligand as an input, and automatically, you know, the software, Autodock or all the software, they generate multiple conformations. And then incremental construction that is used in Flexes. This is another molecular docking software, Flexes. So it splits ligand into base fragment and side chains, and then you place the base, then add the side chains to grow and score as you go. Okay. And in general, use a very basic van der Waals set function. So that's very good actually. Yeah? Often see variability with input conformance. That's not good. Where most of the current research is focused is the scoring function. Okay. The more sophisticated scoring function take longer time. That is the problem. So it should balance need for speed and accuracy. Virtual screening needs to be very fast. So for virtual screening, you really cannot use very complex scoring function. Because for the virtual screening, you are using millions of compounds. If not million, at least more than 100,000 compounds you are using. For molecular docking, you use generally 10, 20 or 50 structures. For that one, you can use better scoring function, okay? But for virtual screening, no, it has to be very fast because you are using more than 100,000 or millions of compounds. And then studies on single compound can be slower, of course, because you can afford it. Because once you fix that, okay, this is the ligand that could be a possible drug candidate, then of course you can use best possible method. You can afford time, okay? So better to then do the multi-stage strategy, actually. So the first thing that we do in multi-stage screening, so that this is how we do it in Schrödinger software, okay? So Schrödinger has a software called Glide for evaluating this binding free energy or for molecular docking study. So when you have 2 into 10 to the power 6 compounds, okay, your database say compounds 2 into 10 to the power 6 compounds, you use Glide HTVS, okay, high throughput virtual screening. And here, to screen each compound, you need 10 seconds. So that means to screen 2 into 10 to the power 6 compound, you need 2.3 days on 100 CPUs. Okay. Now it will reduce you to 2 into 10 to the power 5 compounds. Now you use little bit better or little complex scoring function. Now you use Glide SP. Okay. So this is Glide SP is the Glide standard precision. So now you just check it. Now in this case, it takes 120 seconds per compound. So you can imagine, first it takes 10 seconds per compound, now it is taking 120 seconds. 12 times more time it is taking. So then the third stage, you use glide XP, that is the extra precision model. And then here you see that it takes 10 minutes. So for glide SP, it takes 2 minutes, and for glide XP, it takes 5 minutes. So the time is increasing significantly. So that is why you can use this multi-stage approach for the calculation. If you use glide XP for the 2 into 10 to the power 6 compounds, then you know that how many times you need. So instead of 10 seconds, there you will take 10 minutes. Okay? So that is the problem. Now, generally for drug discovery, we have this 2 into 10 to the power 6 database. We start from there actually to find a single compound which we think would be a potential drug candidate. Okay? So now glide XP will give you 2 into 10 to the power 3 compounds, and then you can do the visual analysis, further refinement, synthetic considerations. From there you can do it. Actually, from 2 into 3, you can again further refine it based on their structure activity relation, admit properties, all those things you can again use as a filter and reduce this number to a greater extent. Okay, and then with this reduced number of compounds, you can go for synthetic considerations. That is, you can ask a chemist, okay, why don't you synthesize this, so that we can go for real testing. Okay, so generally in practical, we use these multi-stage screening approaches. Okay, and the scoring method, as I said, that at different level, we are basically, when I say that glide HTBS, glide SP, glide XP, basically the scoring function changes. Okay. So the binding process that leads to the formation of a complex between a ligand and its receptor is controlled by several factors. Okay, so those are called the different interactions that compose these things. Okay, the interaction energies between the two molecules, the dissolution and solvation energies associated with the interaction molecules, and the entropic factors that occur upon binding. The final energy of binding will depend on the overall balance of these factors. Just think about it. So this protein ligand binding, okay, the protein drug interaction, you can study it using experiment also. You just solve the crystal structure of the complex. It is difficult to obtain, but you can do it. So once you get the crystal structure of the complex, then you can visually inspect it and you can find what are the different interactions. Okay, but really, then what you are missing there? You are missing two aspects. You are missing the dynamic part. Previously, we say that the structure determines the function. Now we say that it is the dynamic structure function relationship. Okay? The evolution of the structure with time, that determines the function. A kinase that can remain activated or inactivated also, okay, because there is a conformational changes. So that's the thing. And another thing, when you solve the crystal structure, then you are using some buffer solution. You are really not considering the real biological environment. Real biological environment is aqueous or it could be membrane. So that is actually the solvent part. So you are missing that part in experiment. So take into account that thing. We can use computational methods. So a good scoring function should take into account that part. Okay, this solvation part also. Now, just remember one thing. I said that we often tell that if the ligand forms more number of hydrogen bonding with the receptor, you will have a stronger binding. That may not be the case. And here lies the answer actually, the solvation part. Why? Because if the ligand forms hydrogen bond with the receptor amino acid, then basically you are kicking out the water molecules from that. Otherwise, it will have interacted with water. So that means there is a penalty that is arising because of the dissolution of the polar group. That is a penalty. So penalty means that will always disfavor the complex formation. And then there is another penalty. Since you are kicking out the water molecules so that they can form hydrogen bond, there will be entropic penalty also. That is also disfavors the complex formation. Not only that, there is another thing. The protein and ligands both are free molecules. They can rotate, they can vibrate, they can translate. But when they form the complex, when the ligand binds to the binding cavity and it got stick there, so that way they are losing rotational, vibrational, and translation degrees of freedom. That is also a penalty. That will be actually, that is called the configurational entropy. That will also disfavor the complex formation. Okay. So what will then help you to bind? The electrostatic, intermolecular electrostatic interaction, that will favor the complex formation. Then van der Waals interactions, that will favor the complex formations. And then the non-polar component of the solvation free energy. Okay, that will also favor. Otherwise, the polar solvation free energy and the entropy, they will disfavor. So the overall binding will depend on how these interaction energies are balancing each other. Okay, so your scoring function should effectively calculate all these parameters. But entropy calculation is not easy. It's a very time consuming thing. Okay, so now what are those different interaction energies? So I already told that there could be electrostatic interactions, there are hydrogen bond interactions, van der Waals interactions, and hydrophobic forces. So they all favor the complex formation. Okay. So the scoring function is generally shape and chemical complementary scores, empirical scoring. It could be force field scoring, which is based, knowledge-based scoring, and then the consensus scoring. Okay. So shape and chemical complementary score is very easy. So you divide the accessible protein surface into zones, hydrophobic, hydrogen bond donating, and a hydrogen bond accepting part, and do the same for the ligand. Okay. Then find ligand orientation with based complementary score. And empirical scoring, as you see, generally Flexes, Ludi, Hammerhead, they use this kind of empirical scoring function. So it has all those different parts. Okay. Entropy, hydrogen bonding, ionic interactions, aromatic interactions, hydrophobic interactions. They have taken into all these different interactions. Okay. The base thing is the force field. So if you use Amber force field parameter, that is best because here you are taking into account the angle bond, okay, the bond stretching, angle bending, torsional changes, then the van der Waals interaction and the electrostatic interaction, all possible you are taking it. This is the best, but this is very time consuming, so we don't use it actually. Okay, so that is the thing. And different search algorithm, I told you already that exhaustive search, Monte Carlo search, genetic algorithm, simulated ironing, taboo search. But the main thing problem is summarized here. For protein drug docking or protein folding problem in computational biology overall, the problem is because of this figure that I have shown you. All the method that we developed just to tackle this problem. So this is the phenergy, inherent phenergy landscape of the protein. And you see that it's a valley. There are a lot of these valleys are there, okay? So those are local minimas are there, and finally the N is the native state. you want to go to that region. The problem is that you got stuck in all those local minima and you may not be able to go to the native state. So native state would be for which this protein ligand complex has the lowest energy. But when you perform the docking, most likely you get stuck in those local minima. Okay, so all this search algorithm means basically how can you reach from those local minima to the global minima. It's an optimization problem, basically. Okay, for that, that's why we use different method actually. We use Monte Carlo, MD simulation, and sometimes the hybrid approach, we combine Monte Carlo and MD simulation together. So all different statistical mechanical approaches have been developed to basically overcome this problem. So this figure you should always remember. This is the problem that we face in computational biophysics, or protein drug designing, all those things basically. How you can effectively overcome the local energy barrier and reach to the global minimum. Sometimes the barrier height is too high that you cannot overcome by traditional simulation. So then you have to use some enhanced sampling technique. You have to give a biasing potential, okay, so that you can overcome. You know that if you want to really cross a high energy thing, like if you want to cross the wall, then you ask your friend to give you a push. Similarly like that, you give some push, give some barrier, this potential energy actually, okay, extra force that you give. Enhanced sampling that we say. So, but then the problem is that once you, okay, you are biasing it, you are telling, okay, you move this way, so you are giving a bias. But now when you want to calculate the equilibrium properties, then you have to unbias it. You have a simulation which is biased, you have to unbias it, then only you can calculate the equilibrium properties, okay? So that is also, there is a different technique how you can get unbiased to bias result, okay? So those are beyond the scope of this course. But overall, just to remember that this is the problem that we face in computational biology and how we can tackle these things. In simulated annealing, we just do the same. What do you do? So suppose there is a barrier. To cross the barrier, what you need? You need energy. What is energy? If you increase your temperature, you will have more energy because the atoms will vibrate more. More vibration means their velocity is more. More velocity means they have more kinetic energy. They have more kinetic energy, of course, then they can cross the barrier. So exactly that you do in simulated annealing. You increase the temperature to high temperature. Instead of, generally the room temperature is 300 Kelvin, okay, you increase it to 400 Kelvin, not 500 Kelvin. Okay, now you have a high temperature. It has a lot of energy. Now you reduce the temperature. You anneal it. Okay, you anneal from 500 to 300 Kelvin. So automatically you are coming from high energy to lower energy state. So you can always overcome those barriers and you can reach to the native state. That exactly you do. And taboo search, well, I mean, this is stochastic search algorithm. Okay, taboo means prohibited, don't go. Once a confirmation is visited, you said, okay, this site is this confirmation is taboo. That means I will not visit. I will only visit to new confirmations. Okay, so that means that will help you to search all possible confirmations because you are not repeating the same confirmations. Okay, so all these different algorithms have been developed to find the best possible matching actually. The best possible binding pose. Okay. Now, I told you one thing that I will tell you that generally for molecular docking, this is a tendency that we say that the best docked structure corresponds to the lowest energy. Okay, so if that is the case, then in this figure, the first minima that you see, that should be your best docking pose. But that's not the case. You need to look into other thing also. Now look at this, the real site. Okay, where I have shown this thing. The lowest energy site, the barrier height is 10 kcal per mole. And the real side, the barrier height is 15 kcal per mole. So which one should be the real, the best? Where the barrier height is 15 kcal, because once it is bound there, the barrier height is so high that it cannot come out. So once it binds, it will remain there. That means it will have a tighter binding. So that is the best pose. So having lowest binding energy does not mean that is the best pose. You need to look at the structure also. You need to visualize the structure and see. Okay? So like if you start from here, so you say that this is your base structure, and now you run molecular dynamics simulation from here. You will see that if you run a very long time scale molecular dynamics simulation, you will see that the Yoa's ligand is coming out of the binding site. It will not remain there. But if you do a long time scale dynamic study for the second one, which I say the real binding site, which has a barrier height of 15, it will remain there. It will not come out. It means the structure is more stable in that stage compared to the first one. Okay? So you have to be very careful. Just because the predicted binding energy is lower, no, you should not use. So that's why previously it was the case. You would just do docking study and submit a paper, people used to accept it. But now it is not like that. You do docking, virtual screening, then docking, all those things you do it. Then you have to supplement your finding by conducting molecular dynamics simulation. You have to show that you are saying that this is the predicted structure, predicted pose. You have to show by conducting MD simulation that it remains stable there. You need to show that the ligand is not coming out of the binding pocket. Then only you can go ahead and do the experimental testing, and you can say that you have a drug candidate, potential drug candidate. Okay, it's not a drug candidate, it's a potential candidate. Okay, so that is the one approach that you should remember, and I will finish it quickly. Okay, so now what makes a good docking target? This is very important. Okay, you have a molecule, now you want to dock it. So where to dock? How do you find that, okay, it's better instead, because in protein surface you will see a lot of small pocket. Okay, so which one to choose? That's very important. Okay, so you need to choose deep, well-defined pockets. Shallow pockets have too many options. Okay, so you should not choose that. Well, I mean, if you have a peptide inhibitor, then of course surface is a better choice. But generally for small molecule, we need deep, well-defined pocket. And then sites for specific interactions that has, say, many charge or hydrogen bonding sites are there, or mostly hydrophobic van der Waals interactions are bad actually. Okay, there should be some charge interactions also there, so that it can form hydrogen bond. Hydrogen bond is required, but too many hydrogen bond is also not good. Okay, and then well-ordered side chains. So this is my final slide. I'll stop here, the theory part. So this is all those things. So now the docking thing, you know, virtual screening, you know how to find the drug molecules. So now how do you know basically that whether it's a drug candidate or not? Okay, so drug likeness with a simple counting method. Okay, this is called rule of 5. This is called Lipinski's rule of 5. So the molecule that you find should satisfy these 5 conditions. So you can put additional filter in your simulation, or I mean in your molecular modeling, docking, so that you can reduce the number further. Okay. So one is this octanol water partition coefficient. Okay, that's the log p value should be less or equal to 5. Molecular weight, generally small molecule. Okay, so molecular weight should be less than 500. Number of hydrogen bond acceptor less than 10, and number of hydrogen bond donors less than 5. And if 2 or more of these rules are violated, the compound might have problems with oral bioavailability. Okay. So this is the Lipinski's rule of 5 that it should follow generally. Okay, so that's all. And just one more thing I would say, that computational docking has this, I'm continuously telling you, okay? It's always about trade-off between efficiency and accuracy, more effective scoring functions, and better model of flexibility. That's what you require, because that is the limitations that you have in molecular docking. And that's why molecular docking is not enough. You have to do MD simulations. If in your molecular docking, you can take into account the protein flexibility, full protein flexibility, and the best scoring function like the that we use for AMBER MD simulations, then you don't need to do MD simulations actually. You'll be pretty much sure that whatever I'm predicting is correct, but that's not the case. You are not doing it. So that is the bottleneck, and that is what the research still can be done. How we can effectively take into this. Okay, so this field is still open in these areas actually. How to treat the flexibility in a better way, and how better and effective scoring function that you can use, which can be better at the same time faster also. So that means you can parallelize it very effectively. Okay, and this is the thing, that accuracy is depending basically decreases for high throughput virtual screening. Okay, you use large number of molecules and the accuracy is very low. Okay, docking is somewhere here. You can see that it is accurate, but for docking you use very small number of data set, very small number of molecules that you use. Now for MD simulation, even you use further less. Okay, but its accuracy is very high. Okay, so that's all, and these are the popular different software that is available. Okay, rigid body, quasi-flexible, and flexible models. So these are available. Okay, thank you. Now you can ask me questions if you have.
Yeah.
I'm ready to answer.
Yeah, sir. Thank you, sir. Thank you for your nice presentation of this session. Now it's for the audience to ask their doubts. You can unmute your mic so that everybody can hear you, or you can put it up in the chat box. So I would like you to unmute and ask the question. That will be better.
So I see that someone asked how a drug can be flexible. I mean, it's a small molecule. So small molecule, drugs are small molecule, it should always be flexible. It generally wiggle around the binding cavity. See, that's why you have to design your small molecule based on the binding site actually. Okay. If your binding site is big enough and you are inserting a very small molecule, okay, your drug is very small, what will happen? It has a lot of space to wiggle around. It will move around. That will be a very good binding. Okay. What you need to do is to make a better, little bit big molecule so that it's smartly fitted into the cavity. Once it attaches there, it remains there. Okay. You need to maximize the interactions. You need to maximize the hydrophobic interactions. That is the van der Waals interactions. You need to maximize the charge-charge interactions. Okay, so that overall interactions should be, the energy should be minimal.
Sir, there are a few questions from Shamlan. He asks, which is free and user-friendly docking software?
Which one is Autodock is user-friendly. Okay, of course, that one is and also Schweidinger software, that is also very user-friendly, but that is a paid version. Okay, Schweidinger is paid, and Autodock Vina is free. So tomorrow, and now one Resmi Ranjan has asked, can we have a practical session on the docking software? Yes, Resmi, we'll have, tomorrow we'll have practical session on molecular docking, okay? I will send, okay, so what you need to download, I'm just writing on the chat box, these two software you should download. So tomorrow we'll have a lab session, okay? Just download Chimera and download and Autodoc. Not Autodoc Bhina, only Autodoc, okay? Download these two software and install it in your laptop, Chimera and Autodoc. Tomorrow, I have session, I think, from 11 o'clock. So I will do the Autodoc, this tutorial, okay? How to do docking. We'll take the example because these days everybody is working on COVID. So we'll take example from COVID, okay?
Yes, sir. Tomorrow, 11 to 12:30 we are having.
Yeah. So tomorrow we'll do the docking study. The practical session will be. Now, what is the meaning of ensemble? Means it's a bunch of conformations. The same protein, but with different conformations. That is called ensemble. It's a statistical ensemble that you can see. Okay? And stochastic is randomized thing. It's not deterministic. So tomorrow we'll first do, I will show you first this free software, Autodoc and Chimera, how to do it, docking. And then we'll also show you how to use the commercial software, that is Schrodinger. Because in the industry, people use Schrodinger. Okay. So I'll show you both, how to use. In my research, I use both actually. I mean, so don't think that Autodoc, it is free, that's why it is not that good. It is good. I mean, still you can publish paper with that. So I request you all to download these two software, okay, Chimera and Autodoc. Please download and install it.
Yeah, participants, any other question? Yeah, I think there are no questions. So now let us thank our expert, Professor Dr. Parimal Kar, on behalf of our director, institute, and participants, as well as the chair for today's session, Dr. P.K. Swain sir, and myself. I thank you very much for this wonderful session. Thank you, sir. Thank you. Thank you.
Yeah, you're
And,
welcome.
yeah.
And thank you all.
Yes,
Thank you, sir.
Thank you. Thank you. Okay, see you tomorrow.
Yes,
And
sir.
tomorrow we'll have practical
Yes, sir.
session. Okay, there is no theory. Tomorrow we'll do practicals. Okay.
Sure, sir.
Okay. Bye for now. See you.
Okay, participants, you take a break and join us by 3:25. And I thank our chair, session chair, Dr. P.K. Swain sir. Thank you for joining us in this short notice. So if you have any questions to him, you can pose. He is the HOD of the Basic Applied Science Department. He is basically a physics guy. So if you have any questions, you can pose. He will be there for 1 or 2 minutes. Okay, then I think there are no questions. Thank you, Swain sir, and thank you,
you, sir.
participants. Yeah, take it as a tea break. So since this is online, it is a tea break. Okay. Thank you, participants. So join us by 3:25 for the next session. Don't forget. Okay.
Okay. Thank you.